G'day viewers. In this segment we'll talk about hierarchical routing. So our topic here is really how to scale routing to very large networks, and the technique we're going to use is hierarchy, where we route not to an individual node but to a large region of the network. So before we get into that, I'd like to give you a little bit of motivation. Here's a slide you've seen before about internet growth. We're growing very rapidly. There are now more than 1 billion internet hosts and growing. And of course, the previous slide was just the number of internet hosts. This slide shows the growth of the internet routing tables, which are the tables which are maintained in routers to be able to forward packets to all directions. This table is also growing very rapidly. You can see pretty much exponential growth. And just looking at the axis, right now, as of about 2013, the number of IP prefixes in a router in the middle of the internet that's got to be able to reach everywhere is around 450,000. That's a lot. The impact of all of this routing growth is bad in pretty much every dimension you look at. You might look at the size of the forwarding tables that need to be kept in memory. That's growing. That's the one that's reached 450,000. That means both larger tables, so more memory in routers, and it could potentially mean an increase in lookup time depending how it's done. As well as the size of the forwarding table itself, another concern is the number of routing messages which need to be sent around. As there are more places and addresses to reach, the number of routing messages continues to grow. And it can actually grow very quickly because not only are there more locations, but we need to be able to inform every node about what's going on in terms of paths to reach every other node. So there's a lot of growth there. And finally, the routing computation itself grows. If every node gets to learn enough about a topology to be able to compute routes, the computation over this graph grows faster than the size of the network. It's superlinear in terms of the amount of work that needs to be done. So this is all bad. Routing growth is going to stress the network. We would like to come up with techniques to scale routing so that it can more gracefully handle a large network. What are those techniques? Well, I'm glad you asked because I've written them down here. In fact, we've seen some of them. The first technique here is the use of IP prefixes, where we don't have an entry in the table for every individual host. Rather, we have an entry for a block of hosts called an IP prefix. We've seen how IP prefixes work. In this segment, we're going to talk about network hierarchy, which is the routing to the different regions of the network. And then, in a future segment, we'll talk about IP prefix aggregation, which essentially are more games you can play to join or split prefixes that use hierarchy in different ways. We'll see that later. So let's look at hierarchical routing. That's our focus here in a little more detail and find out what it actually is. So the overall goal here is to introduce some kind of larger routing unit and be able to structure tables so that they send packets towards that unit. We've already seen that we now have IP prefixes, which are groups of hosts. That's a larger routing unit from an individual host. That's great. We want to build on that. And we'll build on that by introducing the notion of a region of the network. This might be a complete ISP network, for instance, but I'll just call it a region for now. And we would like to change our routing procedure so that we route first to the region, and then when we've arrived at the region, we route to the particular node within the region. This is really no different than, to pick a real-world example, navigating by driving to the city you're trying to reach, and only when you get to the city, trying to find a particular address and worrying about how to get around the city. What we're doing here, really, the gain that we'll get for routing is that we'll hide the details that are internal to the region from everyone outside of that region. Well, I'm sure you get the sort of theory of how we could use hierarchy in regions, but let's go through an example to make some of this concrete and make sure we understand it. So I have a network here on the left, and you can see that there are 5 different regions, and within each region there are a few nodes connected together, and the regions are connected together too. Now, every node in this network is going to have its own forwarding table so that it can send packets in different directions. The forwarding table here is shown for node 1A. That's this big long table. You can see it lists all of the other nodes and which output line, which next hop to get there, and how many hops away. So this is shortest path where the distance is simply the number of hops. So this is the kind of table you would get, this large table, if you use the techniques we have so far. On the right, I have the hierarchical table for 1A. Now you notice in this table, it lists in detail, it has the same entries for entries within region 1, because it's 1A, that's 1A, 1B and 1C. Well, 1A, not hard to get to since you're already there. However, the other entries have been collapsed. If you look at the full table, it had 4 entries for network for region 2. That's collapsed into a single entry. We don't care about differences here. We just want to know which way to go to get to region 2. Similarly, region 3 has been collapsed into a single entry, and region 4 and region 5. Oops, my arrows are a little off there, but you get the idea. Okay, so we now have a much smaller table. We can also use it to route. Let's just see, here we have a packet that's trying to go from 1A to 5C, and I've colored in those nodes just so you can see them on the graph. At 1A, we can look up the decision for 5C. Now, since this is a hierarchical table, there's no entry for 5C in particular, there's just a blanket entry for 5. It's this last one. It says to get to region 5, go via 1C, and it's going to be 4 hops. So we'll go here. We don't have the table for 1C written down, but the reason we went here, of course, is to go this way. And you can imagine that the path we will take to get to 5C, that's this path. Let me just clean up this figure. Okay, so you can see the path we took to get from 1A to 5C. And we could perform the same exercise for different paths through this network. But I chose this path for a reason, and that's to illustrate the penalty that we can pay sometimes when we use hierarchical routing. For most of the paths we're using hierarchical routing, their distance that we take in hops when we follow them is the same, even if we didn't use hierarchical routing, and we've just got a smaller table. But for some paths, we can actually end up taking slightly longer paths than the shortest possible path. That's the example here. Now you can see in the full entry, the full table, from 1A, if I want to go to 5C, it's this entry here, it says I can get there in 5 hops going via 1B. And you can see I've put in blue on the diagram the path we would have taken to get there. And you can count it and you can see that it's 5 hops. However, in the hierarchical routing version, the best route to get to region 5 is simply given here as 1C, and that took us along the other path. That's because we've forgotten about all of the detail inside region 5, and we simply wanted to get into region 5 as quickly as possible. So that's the penalty we might pay sometimes. And just to close on this, I'll make a couple of observations about hierarchical routing, just to reinforce the concept. So the main concept here is that outside a region, every node has a route to all hosts within that region. We're hiding what's inside that region. We don't worry about it when we're far away. This is what gives us the savings in table size. They can be substantial. It's also a savings in terms of messages and computation. We also get benefits there, even though we didn't look at them in detail. One thing I want to point out, though, because it's sometimes a source of confusion, is this doesn't mean that all nodes inside a region need to take the same path towards another region. They typically don't. Every node has a path to a region for all destinations in that region, but every node could take a different path to reach the same region. And the reason for this is that routing decisions are still being made individually by nodes. It's just we're looking at the routing decision to reach an entire region. There's no notion of taking a single decision that everyone within a region has to follow to get somewhere else. Okay, now you know about hierarchical routing.